Okay, so this is just a continuation of the previous clip. It's the same title with the additional word examples. We want to do some examples. So let me repeat the idea. Somebody gives us a field. That's what the examples are going to be about. Somebody gives us a field and asks us about calculate some line integral. If we don't know anything about the field, we can still calculate the line integral using the definition of a line integral. We have to find the parametrization of the curve, calculate the field on the curve, find the derivative of the parametrization, r prime, do the dot product, and so on and so forth. We know how to do that. We've done examples. If we know that the field is conservative, then we have a cool shortcut. All we need to do is find the potential function and the difference in potentials between the two endpoints of the curve. Okay? So the procedure is going to be the following. Given f, we're going to first check if it is conservative. Usually checking is easy following this property number 4. Okay? If it is, great, we can move on. If it isn't, well, none of this is going to be relevant. If it is, we're going to find the potential function, okay, and that's not something too sophisticated. If you think for a minute, f is the gradient, so we need to find phi such that its gradient is f. Okay, that's kind of an antiderivative sort of procedure, right? And once we know phi, answering the original question, the line integral, is easy. In fact, for any curve, we don't care about a and b. We have all for the price of 1. Okay? So let's do some examples. So example 1, let's look at f is going to be e to the power xy. That's going to be the I component, plus e to the power x plus y, that's going to be the j component. So this is p of xy, and this is q of xy. Right? Each of which is a scalar function. And we want to know, first of all, is this a conservative field? Okay. Clearly f is C1 on R2, on the entire plane. Do you agree? So the whole business of being simply connected and C1, that's all a non-issue here. All 4 conditions in the theorem are equivalent. Does everybody agree? Okay. So what we want to check now is qx equal to py. Let's check that. So what is qx? Qx, the derivative of q with respect to x, is e to the power x plus y times the inner derivative, which is 1. Do you agree? Py, or let's write it like this, suggestively. Py, the derivative of p with respect to y, is e to the xy times the inner derivative x. And they're not equal. This is not the same function, obviously. Do you agree? And the conclusion is that f is not conservative. And therefore, the power of this theorem is irrelevant to this f. If somebody asks us to calculate some integral of this field, some line integral, we'll just have to do it the usual way. Okay, clear? Okay. Example 2, let's look at the field 2x cosine of y, that's going to be the I component, minus x squared sine of y, that's going to be the j component. Once again, this field is C1. All the derivatives are going to be continuous partial derivatives on the entire plane. There's no issue here. Okay? Let's check if qx equals py. So what is qx? Well, what is q? This is q, and this is p. Right? So what is qx? The derivative of q with respect to x is minus 2x sine y. What's the derivative of p with respect to y? It's minus sine y times 2x. It's the same. Do you agree? So this specific field is conservative on all of R2. Is conservative on the entire plane. Clear? Great. So now let's find its potential function. Since it's conservative, we know it is the gradient of some function phi. Okay. So therefore, there exists a potential function phi. Potential in the sense that f is the gradient of phi. Right? Let's find it. How do we find it? What does it mean that f is the gradient of phi? Well, it means that, where's f? This is f. We know, let's write it here again. We only wrote it several times, but one more is never harmful. These are the components of f. These are the components of phi. And they're equal. So saying that f is the gradient of phi means that p is the derivative of phi with respect to x, and q is the derivative of phi with respect to y. Right? Okay. What is p? This is p. So d phi to dx has to be equal to p. That's the statement that f is the gradient of phi. What is p? P is 2x cosine y. What are we looking for? We're looking for phi, right? We're looking for that potential function. So phi has to satisfy that its derivative with respect to x is this. We know the derivative, we want the function. Let's say that again. We know the derivative, we want the function. We've done things like that back in Calc 1. That's what we called antiderivatives, or indefinite integrals, right? Finding the antiderivative. So, move. Phi itself is going to be the integral, the indefinite integral of this thing, of its derivative, dx. Do you agree? Because this is the derivative with respect to x, therefore the antiderivative with respect to x is going to be the function. Clear? So let's see what we get. We're looking for the antiderivative with respect to x. Cosine y here is just here to confuse us. What's the antiderivative of 2x? X squared. So it's x squared cosine y. The derivative of this with respect to x is precisely this, right? Is this done? No. What's missing? Plus c. Do you agree? What was c? Hint, it starts with a c. Right, c was a constant, remember? Why was it there? Why did we add plus c? Because we said a very simple reason. We want something whose derivative is this. If we add a constant, the derivative is still going to be this, because the derivative of the constant 0 doesn't contribute anything, right? But here, it's a bit more delicate, because we're looking for a function in x and y. If we add here not just a constant, but any expression which only has y's in it, no x's, any xless expression here, its derivative with respect to x is going to be 0. Do you see that? So it's not just plus c, it's plus, let's call it g of y. Any function of y would still satisfy this. Do you agree? Everybody? So we know phi, but not entirely. We know this is the only component that can have x's in it, but phi could still have another component which only has y's in it, and it will still satisfy this. Do you agree? So how do we find g of y? We use the second part of the data, which we haven't used yet, which is that q is the derivative of phi with respect to y. Okay? So here we use the fact that p is the derivative of phi with respect to x. Now let's use the fact that q is the derivative of phi with respect to y. So let's write that. Q equals d phi to dy. Therefore, let's write what we know. Q, in our example, was minus x squared sine y. And this has to equal, this was q, this has to equal d phi to dy. Okay, so move with me one board back for a second. This was phi. This is the candidate for phi. I want its derivative with respect to y. What's its derivative with respect to y? Well, it's minus sine y times x squared plus g prime of y, whatever that is. Do you agree? Minus x squared sine y plus g prime of y. Minus x squared sine y plus g prime of y. Do you agree? So what can we conclude from this, from these two things having to be equal, that in this example, g prime of y has to be 0. Okay? G prime of y is 0 in this example. And what does that mean about g itself? Right, it turns out that in this example, g is in fact only a constant. It's y-less and x-less. So in this example, g of y is in fact a constant, some c. Okay? And now we can end this line of argument and say that phi of xy is x squared cosine y plus c. We have some liberty here. We can choose whatever c we want, and that's going to be a potential function. The potential function is not unique. It's unique up to a scalar, up to an additive scalar. Clear? It's never going to be unique. It's always going to have this scalar degree of freedom, because all we know about phi is its derivatives. And those derivatives don't see the scalar. They annihilate it right away. So, clear? So this is our phi. Okay? Clear? So now we have the potential function. And we knew it would exist because we know that the field is conservative. And now, how do we use this? So the standard, and these are very standard questions. In every exam you have a question like this. You get a field and somebody asks you, find the line integral of the following field, or maybe stated in the physics interpretation, find the work of the force given by F equals pam along the curve connecting the points A and B counterclockwise when looking from above along the path pam. So it takes an hour and a half to decipher what you need to calculate the line integral of. But if you think for a minute and you verify and you see that it's a conservative field, it all becomes completely unnecessary. So here's an example. So for this example, if we want to calculate, to find, for example, the integral over gamma of f dot dr for this example, where gamma connects the points, let's say 1, 0 to 0, 1 along the unit circle counterclockwise. Love this word. So we want to connect. Remember what f was. F was 2x cosine y and x and minus x squared sine of y. That was f. We need to parameterize the circle. That's not too difficult. We know how to do that. Then we have to make sure that the parametrization goes counterclockwise, connect these 2 points, and calculate the line integral. Not that bad. Do you agree? But now, since we know that f is conservative, we have a shortcut. This integral, the required integral, is what? Is phi at the endpoint b minus phi at the starting point a. That's it. Right? That's what we know from the theorem about conservative fields. They satisfy this. Do you agree? Everybody? Okay, so where was phi? Here's phi. We don't care what c is, because it's going to cancel out in any event. So usually it's just easy to choose c to be 0. Makes things simpler, but it doesn't matter. What is phi at 0, 1? When x is 0 and y is 1, this is just 0, minus. When x is 1 and y is 0, cosine of 0 is 1, 1 squared is 1, 1 squared times 1 is 1. You get this. And that's it. That's the line integral. Easy, right? And now if somebody would tell you, calculate the same thing, but now gamma connects these 2 points along some crazy serpentine that goes like that, who cares? That's the work. Good? Question, yeah.
If it was clockwise, was only to invert the like.
Right. If it was clockwise, in terms of the drawing, it would be going like this. But in terms of the calculation, it would make no difference, because the whole point. Let's go back to the theorem. The whole point is, if it's conservative, then it's the gradient, in which case any line integral depends only on the endpoints. If you're going from A to B, it's the potential at B minus the potential at A, and you don't care in which direction you're going, what path you're taking, how you parameterize it. Everything becomes unimportant. It's just the difference of the potentials at the endpoints. No, well, if you change A and B, then it's going to have a minus sign. But if you're going from point A to point B, it doesn't matter if you go like this, or, can you see me? It doesn't matter if you go like this, or you go like this, or you go like, I'm having fun here, this. Same work. Questions? Okay, so this is the idea here. I want to just make one final remark before we move on. So for this, remember that we required that the domain is simply connected and the field is C1. There are slightly stronger versions of this theorem that allow you to be a bit more flexible regarding these conditions. Okay? I'm not going to write them formally and prove them, but they go along the same idea. I don't know if you remember that when we discussed that famous field, minus y over x squared plus y squared and x over x squared plus y squared, or minus x and y, I don't even remember which one it was. And we said if you take a domain, you can cut a little hole in the middle and then do the same arguments and everything works. Remember that sort of argument that we had? So using that same sort of argument, you can have a statement of this nature, that if Qx equals Py, and there is some curve around the hole, so you're not simply connected, there's a hole, but there's some curve around the hole over which this is 0, then it's going to always be 0. Then the field is conservative. Okay? So you can't just say it in general. This doesn't imply in its own that the field is conservative. But if you know this, and you know that there's some field for which there's some curve, one single curve around the hole for which it's 0, then it's always going to be 0. That's exactly the same sort of argument we did in that example. Okay? And I'm not going to write it, I just want you to know that it generalizes this a bit, and it can be used. And it's useful for, you'll see many examples, like for example the gravitation field does have a singularity at the origin. Okay, and so in general you can't use this because it's not defined at the origin, and therefore this fails. But using that generalization, you can still use it. Okay, so that wraps up our discussion of conservative fields in 2 dimensions. Okay, and in fact it wraps up our entire discussion of 2 dimensions. And what we want to do now is move one direction up. So instead of lines, line integrals, the 2-dimensional analog is going to be surfaces. So now we're going to have surfaces, and we're going to want to parameterize surfaces and to integrate over surfaces and to have the generalization of whatever Green's theorem was, and that's going to be called Stokes' theorem, and this discussion and all of that coming up next.